Welcome back to Tightwad Workshop. In our last episode we restored these 3 old bit braces to working condition. So in this video we'll be repairing and sharpening this set of bits to use in them. I've accumulated these bits over the past few months from garage sales and trash and treasure markets. And they're a fairly random selection of types, so maybe collection is a better word than set in this case. The average price for these used bits where I live is about $2 to $3 each. Now when you're making a hole in a piece of wood using a brace and bit, the process is called boring rather than drilling. Now I'm not entirely clear as to the distinction between those two operations, but I think it might have something to do with the speed at which your cutting tool is revolving in the hole. This is the most common type of bit that I've found. Around here this is called an auger bit, but in some older textbooks they might also call it a twist bit. Our second type of bit is made with a solid central rod with a single spiral wrapped around it. This type is called an Irwin bit. Now, unlike a modern twist bit, the spiral component on these bits isn't a cutting edge. On these bits, the spiral is only used to extract the chips out of the hole. The cutting edges on these bits can be ground into various shapes for different purposes. All of these ones have this pilot screw at the tip, which accurately centres the bit in the hole when you're starting it, and also helps pull the bit down into the hole as you're turning the brace handle. This one is made with a pair of extended cutting spurs on the side, which helps this bit to make a nice clean starting hole. Bits that don't have these spurs tend to leave a ragged edge at the top of the hole. Our next type of bit is this centre bit. This is used to bore shallow holes in timber, and its combination of a perimeter spur and a single cutting edge makes it work okay. We also have this adjustable bit, which uses the same general cutting edge design as the centre bit, and it can be adjusted to a range of different sizes. It also has this long shank, so you could use it for boring deeper holes, although since it doesn't have a spiral to eject the chips, you'd have to pull it out every now and then to get rid of them. We also have this countersinking bit. These are used to shape the top of a hole so that your screw heads can finish flush with the surface. These bits are called nail bits, or screw bits, or half-twist bits. If they're fitted to a small wooden handle like this, the tool is called a gimlet, so they might also be called a gimlet bit. And finally, this is the oldest style of bit in our collection. This is called a shell bit, and it'd be familiar to a carpenter from hundreds of years ago. It's fairly simple to make and easy to sharpen, and since it doesn't have a spike in the middle like the other types of bits, it can be used to bore a blind hole close to the opposite surface of a workpiece, without the hole breaking through. And to round out our collection, we have this screwdriver bit. It looks like the screwdriver bit and the shell bit were part of a set, all made in 1943. And this broad arrow symbol means that they were probably issued in a military toolkit of some kind. I've found a surprisingly large number of these bits with the square shank end sawn off. This was almost certainly done by somebody who was planning to use these bits in a modern electric drill. Unfortunately, that doesn't work very well because the drill's chuck just can't clamp that smooth shank tightly enough to successfully turn the bit inside the hole. Also, these particular bits were designed to turn at 60 RPM, or about 1 turn per second, and they just don't work very well at the higher speeds you get from a modern electric drill. I also have these 2 broken bits. But the good news is that all of this damage can be repaired with just a little bit of metalwork. Let's head over to the lathe and see how it's done. I'll be using this old bolt from the scrap pile to make replacement square ends for the bits. We'll start by clamping it in the collet chuck with about 50mm or 2 inches sticking out. Next I'll loosen the bolts on the compound slide and adjust it to a 6-degree angle. Now we can switch on the lathe and start cutting metal. It's still winter here in Canberra, and the oil in the lathe's gearbox is cold and thick, so the lathe takes a bit longer to start up than usual. The bolt is slightly bent, but that doesn't matter for this job. Now we can use the compound slide to cut a 6-degree tapered point on the end of the bolt. This is a fairly small lathe, so I'm only removing about 0.5mm or 20 thou per pass. Once we've shaped the taper, we can switch to a pointy tool and dig a little channel here. Now we can loosen the collet and pull out another 50mm of stock from the chuck. We're shaping this part in stages because otherwise the unsupported end of the rod will get very whippy. Our tapered rod isn't very well centered now, probably because it has a bend in the rod. This isn't going to be a big deal for the part we're making here, so let's just keep going and shave down the shank to match the diameter of our cut-off brace bit. This axis of the lathe does have a power feed, which means a bit less manual handle turning for this step. Now we can use a hacksaw to part off our workpiece from the stock. Let's take this over to the vise for the next step. I'll clamp it firmly in the vise, holding it by the shank. Now we can form the 4 flat surfaces using a file. I'm using a nice sharp file and smooth, steady strokes. In real time, this whole operation took about 3 minutes, so I'll just speed it up to get through it here. I've left the rounded edge on the corners because I'm lazy, but the brace handle still manages to grip it and hold it securely. I've made this jig to hold the broken bit and our new piece in alignment while we weld them together. We'll be using TIG welding for this job. I'm still very much a beginner at TIG welding, so please ignore any swearing you hear in the next few minutes. For TIG welding, the electric arc is used to melt the metal on the workpiece, and you feed in extra filler metal as required. Learning this procedure is a bit like patting your head with one hand while you rub your tummy with the other. Now we can loosen the clamps and turn the workpiece in our jig to weld up the other side. I'm using an unusual angle here to give you a clear view. Normally my left hand would be blocking the camera here. I think I'll leave that to cool a little bit before I undo the clamps. Well, it's not a beautiful weld, but it'll hold. A bit of work with a file or a grinder will improve the appearance. And you can also use a bluing fluid to match the colour of the original bit, if that's important to you. So now we're finally ready to start sharpening our bits. I do most of the sharpening work with this small square file. For larger bits, you'll sometimes have enough clearance to use a flat file like this instead. And this round tapered file is only needed for the gimlet bits. This type of bit has 2 cutting edges on each side. We sharpen it by filing metal off these 2 inner surfaces here and here. On smaller bits, the curve of the spiral can make this difficult, but this is the correct way to do it. If you have enough clearance available, you can use full strokes of the file, but for most bits you'll need to scrub the file like this. Now we can turn the bit and sharpen the side cutter. It's a good idea to stop and check regularly, just to see how you're going. If you want to get the highest possible sharpness, you can now remove any burrs from the cutting edges with an oil stone. Now we can turn the bit around and sharpen the other pair of cutting edges. We'll test how well that worked in a few minutes. The Irwin bits are sharpened in a similar way, although the different shape of this bit lets us use the flat file instead of the square one. I'll just sharpen the base cutter on the other side, then we'll look at the spurs. The bit rotates in this direction, so we only need to sharpen the leading edge of the spur here. For some reason I got confused and sharpened the trailing edge of this spur instead, so learn from my mistake. We also have enough clearance on this bit to use the flat file instead of the square one. The files left noticeable burrs on this bit, so I'll remove them with an oil stone before we test this one. Our centre bit is sharpened in much the same way as the Irwin bit, but since it only has a single spur and cutting edge, it's a bit faster to do. This bit has some rust pitting, but it should still work okay for boring holes in wood. We'll sharpen the leading edge of the spur on this one too. On all of these bits, it's important to avoid filing the outside surfaces. If you do that, you'll reduce the diameter of the bit, and on bits with spirals, that'll probably make them jam up in deeper holes. The gimlet bit needs to be sharpened along this cutting edge. I find that this is the most difficult type to sharpen well, so I'll just do the best I can. That edge now feels slightly sharp, so I guess we'll see how it works in a moment. The shell bit is the easiest type to sharpen. Once you've set up the bevel with a file or a grinder, you can hone it on an oil stone, in the same way that you'd sharpen a gouge chisel. I'll just use a few light file strokes on this one for now. The countersink bit is sharpened using a triangular file. It rotates in this direction, so once again we only sharpen the leading edge of each tooth. Now that we've sharpened all the bits, I'll set up this piece of timber to test them. We'll start with the auger bit. This is the one that doesn't have spurs, so it leaves a bit of a ragged edge at the top of the hole. It seems to be cutting well, and the chips are being pulled out by the spiral. Unfortunately, all of these types of bits will make an ugly hole when they push through the timber. You'll need to feel around for the right position to clean up the exit hole using the bit's side cutters. Our next test is with the Irwin bit. This bit does have side spurs, so the entry hole should be much more clean-edged. Once again, it's cutting good chips, and the spiral's ejecting them out of the hole. And if I'd been a bit more careful here, we might have been able to use those spurs to cut a nice clean exit hole as well. Now we can test the centre bit. This bit doesn't have one of those spiral pilot screws, so you need to maintain pressure on it while you bore the hole. The single side spur works better than I expected it would for making a nice cleanly defined entry hole. And that single cutter is making nice clean ribbon-like shavings. This bit's only just long enough to reach all the way through this piece of timber, and once again we get a ragged exit hole. Now we can test the shell bit. With these bits, you're supposed to make a pilot dimple to help start your hole in the right place. I was a bit surprised at how quickly and easily that shell bit bores the hole, and manually removing the chips wasn't a big problem either. Once again, we get a bit of a ragged exit hole. Next we'll try our gimlet bit. This was the fastest hole to bore, probably because it's much smaller in diameter than the other bits. The bit was only just long enough to pass through our test timber, so it left a fairly clean exit hole. I'll use that gimlet bit again to make a pilot hole for testing the countersink bit. We can make the countersink as deep as required. I'm just going to leave this one fairly shallow. Now we can fit a screw and wind it in using our screwdriver bit. So now that I have a brace and a 3/4 inch bit, I can finish boring the dog holes in the legs of my workbench. These will be useful for clamping wider boards to the front of the bench, using a holdfast. I don't really want to scrape my knuckles on the floor while I bore that lowest hole, but luckily this brace has a ratchet mechanism to help with that. It's not as fast as turning full circles, but this way you get to keep your skin. Now since we're in the swing of things, I should also bore a set of dog holes into the other side of the workbench. Well, I've got to say, I'm glad that this is a softwood workbench. If this had been made out of hardwood, I might not have survived that upper body workout. I think that covers pretty much everything, but if you have any other questions or if I've left anything out, do let me know down in the comments and I'll do my best to get an answer for you. That's all for now. Thanks for watching. Tightwad Workshop is filmed in front of a live studio audience.